Let's do another example from our conservation of momentum concept here. This one's a little bit different. This one says a 75 kilogram man standing on ice. Stands is standing on ice. One or the other. He either stands on ice or is standing on ice. Does that mean if it's two of them that it means he's not standing, he's moving? He's standing on ice while holding a 2.5 kilogram ball. The man throws the ball forward at 15 meters per second. What's the velocity of the man immediately after he throws the ball? Now let's assume that he's on ice because that provides no friction, which allows him to move backwards as a result of that, right? You guys know from Newton's third law that if object A applies a force on object B, the man applies a force on the ball, then object B will apply an equal and opposite force on object A. Or in other words, the ball will apply an equal and opposite force on the man. So if the ball goes forward, the man will go backward. You also know from an impulse perspective that if the ball has an impulse of +7, let's say, then the man will have an impulse of -7. So that means the man has to go in the opposite direction. This is what I call an explosion. It's not literally an explosion, right? But it's one object becoming two. It's like a bomb exploding and having one piece go this way and one piece go this way. Whenever we have something like that, hey, it's on our always list. Okay, our always do this list. Whenever we have a collision or an explosion, we do conservation of momentum. Let's write down some givens, knowing what we're going to do with this, and then let's start subbing some numbers in here. Let's say M1 is 75 kilograms. Let's say M2, the mass of the ball, was 2.5 kilograms. What else we got? Something is 15 meters per second. What is that? Is that V1 or is that V2? That's V2. That's the velocity of the ball. Is that V2I or V2F? No. That's V2F. Okay, that's the velocity of the ball after he throws it. That's going to be V2F. Okay, what else here? What else do I have, or what am I looking for? Tell me something. Okay, I could say V2I equals 0 because the ball is at rest. Actually, why don't I just say VI equals 0? Because the man and the ball are together, right? One object, the man and the ball. The man is one with the ball. Anything else? Yeah, Matthew? Okay. You know what, I'm not going to write that. You know what, I'll write it down, sure. Technically, that's not a given, right? That's adding them together. And that's something that we can figure out later on. But sure, if you want to do that, go ahead. It's not a big deal. There's one more thing. What am I looking for here? Well, I'm looking for direction, magnitude and direction here. What am I trying to solve for here? What number am I trying to solve for? V1F, right? The final velocity of the man. Now we're going to say PI equals PF. How many objects do we have? Danielle, how many objects do we have before the man throws the ball?
One.
Right, it's the man and the ball. We can write down MT times V initial equals, how many objects do we have afterwards? Two objects, so we're going to say M1 V1F plus M2 V2F. It looks a little bit different than the other problems we've done, right? This time, instead of two objects combined to form one, this time we have one object that's breaking apart into two. MT is, Matthew, I think I said that it was 77.5. What's VI? 0. Like I could have just written down 0 right there if I had wanted to, instead of writing it on that term. 0 is equal to M1, 75.0, times V1F, that's what we're looking for, plus M2, which is 2.5, times V2F, which is 15. Would you expect, here, let me ask you this question for a prediction here. Would you expect V1F to be greater or less than 15? Less, how come? because he has way more mass, right? If the ball gets, what would it be, 37.5 kilograms of impulse, then the man has to get negative 37.5. And since he has a lot more mass, that must end up being because he has less change in velocity. So let's solve for V1F. This is 2.5 times 15 is 37.5. Take it over to the other side by subtracting. Divide by 75, and V1F will be negative, I believe it's 0.50. Is that right? Or you could say 0.50 meters per second. Yeah, backwards, right? 0.50 backwards. Is that all right? All right, what I ask you to do right now is take a look at worksheet number 3 again. This time look at questions 6 and 7 on that worksheet. Okay, let's have a look at number 7 here. Number 7 says a person holding a 15-kilogram gun, a really, really heavy gun, containing one 50-gram bullet, is riding on a train that's traveling at 75 kilometers per hour. Man fires the gun and the bullet moves 350 meters per second to the east. What's the velocity of the gun relative to the ground? There's all kinds of stuff going on in here, right? Firstly, we've got a 50-gram bullet. We could use grams. We could. But we've already got kilograms somewhere else, so we might as well go kilograms, right? The standard unit. Same thing with the kilometers per hour. Okay, we could use kilometers per hour, but since we have meters per second right here, we might as well go meters per second right there as well. East, I don't see any west mentioned there, but we do have an issue here. We have the train is traveling relative to the ground, but the bullet is traveling relative to the train. So I want to draw attention to that as well, because you get two different frames of reference here. The speed or the velocity of the train relative to the ground, and then the velocity of the bullet relative to the train. The velocity of the bullet relative to the ground is going to be different than it is relative to the train, right? Okay? If I'm holding a ball moving in a train, relative to the ground, the ball is moving at the same speed as the train is. But relative to the train, it's at rest. So if I throw it on the train, certain speed relative to the train, different speed relative to the ball. We got to be consistent here. I chose, when I did this question, to do everything relative to the train. But you could have chosen to do this relative to the ground, and that would have been fine. In the end, we're going to have to do it relative to the ground at some point. So I said M1, the mass of the gun, is 15.0 kilograms. And I said M2, the mass of the bullet, is 0.50 grams, or 50 times 10 to the minus 3 kilograms. Or you could have said 0.050 kilograms. Just by adding that exponent there, that scientific notation, it helped me to avoid moving the decimal place over. Now, relative to the train, I said VI is 0. Think about that. Think about this. Relative to the train, how fast is the gun and the bullet moving before it's fired? 0, because it's moving with the train, right? So I said VI is 0. And remember that this is a gun bullet question. The train is just in there to throw you off on the frame of reference. The explosion occurs with the gun and the bullet, not with the train. So the gun bullet relative to the train are moving at 0 meters per second before the explosion takes place. And then we say V2F. I said V2F is 350 meters per second. Relative to the train, the bullet goes off at 350 meters per second. Now, I said that I was solving for V1F. Now, I'm going to put a little star by that, because when I solve for V1F, I'm getting the velocity of the gun relative to the train, but I want it relative to the ground. So I'm putting a star by that, just so I remember that it's not my final answer, but it's well along the way here. So I'm going to say PI is equal to PF. I'm just going to say 0 initial momentum. You could say mt times vi, the bullet gun combined, but we know that relative to the train it's 0, so just sub in the value of 0 there. m1 v1f plus m2 v2f. 0 is equal to 15 kilograms times v1f, that's what I'm looking for here, plus 50 times 10 to the minus 3 times v2f of 350 meters per second. Take this term over by subtracting, and then divide by 15, and I get v1f is equal to negative 1.16667 meters per second. But remember, that's relative to the train. And that's not what I want. So what am I going to do? You guys remember in Physics 20 when you found relative velocity? Remember those questions where the pilot aimed north, but there was a wind blowing to the west? Remember those? When we found a relative velocity, we added vectors. Now, if it was relative in one dimension, we just added. But if it was in 2 dimensions, we had to add using the Pythagorean theorem and trig. We want to find a velocity relative to the ground here. We're going to add these. We're going to say the velocity is the velocity of the train, which is in meters per second, 20.8333. Right, that's the 75 kilometers per hour, right? Plus negative 1.16667 gives me 19.7 meters per second. Okay, let me give you some maybe more anecdotal, everyday experience version of what the vector addition we just did. Okay, you're at the airport and you're on one of those moving walkways. Okay, you know what I'm talking about? Those moving walkways, I'm not sure what the purpose of them are other than to entertain you. Because, like you have to walk a mile in an airport and they give you like 50 meters where they give you a bit of a break. Like, if they really wanted to help you, they'd make it all the way around. They'd have it everywhere, right? But they don't, but. All right, so you got that moving walkway, and that moving walkway is moving at, let's say, I have no idea how fast they move, but just for ease of math here, let's say it's moving at 5 meters per second to the right. 5 meters per second to the right. Okay, if I'm on that moving walkway and I'm moving at 1 meter per second relative to the walkway, then what's my velocity relative to the store over there? 6 meters per second. But if it's moving that way at 5 and I'm walking at 1 meter per second this way, in other words, negative 1, then what's my velocity relative to the store? 4 meters per second, right? Make sense? So we're saying 5 plus 1 is 6, or in the case of moving opposite to it, 5 plus negative 1 equals 4. That's exactly what we did here, right? Train's moving one way, the gun goes opposite, right? And therefore we add it as a negative value.
Why would
Last example of this topic, we'll finish this off here today and start something new tomorrow here. Number 4, last one on your sheet, says a 1,000 kilogram car traveling east collides with a stationary 1,200 kilogram car. This should say, by the way, traveling east at 10 meters per second. Collides with a stationary 1,200 kilogram car. What does stationary mean? Not moving, at rest, right? The two cars lock together, and then they hit another one, also at rest. Now you got 3 cars that are locked together, and they head off as one. What's the final velocity of the 3 cars? Now, bear with me for a second on this. Okay, this sounds complicated, but it's really not that complicated. Lots of people, if they saw this problem on a test for the first time, would say, oh, we got 2 collisions here, right? Do you have 2 collisions? You do. Yeah, car 1 and car 2 collide with each other, and then they stick together, and then car 1, 2 collides with car 3. 2 collisions. So you could say, don't write this down, okay? You could say PI equals PF for the first collision and solve for VF. And then you could say PI equals PF for the second collision, but PF for the first collision would become, VF for the first collision would become VI for the second collision. Does that make sense? You could do that, absolutely. But this is what I call a progressive collision. That's just my name for it, so don't look for that somewhere else. A progressive collision is a collision where we have more than one collision, but still the system is isolated. So outside of these three cars and the forces that act within these three cars, there's no external forces. If that's the case, then we could treat this as one collision. We can say the initial momentum equals the final momentum. There are three cars initially. M1, V1, I, plus 0, plus 0. Right? Why plus 0, plus 0? Well, because the other two cars were at rest. If they weren't at rest, then we'd put in M2, V2I, or whatever. Afterwards, Danielle, what are we going to put in afterwards? All three of them stick together at the end of this. All three of them stick together, so it's going to be MT times VF. Right? So basically what you're saying is the momentum of car 1 gets transferred to all three of them. Mass 1 is 1,000 kilograms times V1I is 10 equals the total mass is 3,400 kilograms times VF. And you solve for VF there, and it works out to be 2.94 meters per second. So don't let something like this bother you, okay? Don't let something like this bother you. It's multiple collisions, who cares? Who cares? If nothing else has come into play in the middle of all this, well, the total momentum stays the same. Before, during, and after. We usually say before and after, right? But before, during, and after. Well, we're just looking at before and after here. Doesn't matter what happened during, the total momentum stayed the same.